Our next speaker, Dr. Tad Hogg, is a colleague of Dr. Merkel's at the Institute of Molecular Machines and also earned his PhD from Stanford. He is working, I believe, quite closely with Dr. Merkel, and following on some of the discussions of earlier this morning in terms of how do we get power to the nanobots, the very great ideas elucidated about use of the piezoelectric effect and the natural energy sources within the body, hemodynamics, motion, kinetics, etc. Dr. Hogg is going to focus specifically on chemical power for microbots and working in the capillaries. So please join me in wishing a warm welcome to Dr. Tad Hogg.
Thank you very much. Thank you. It's a pleasure to be here and join this discussion of nanorobotics and for uses for medicine. I hope to learn a lot from you over the next day or so of other kinds of applications that we might look at for nanorobotics. What I'm going to be describing today is one particular problem, and that is how might we power tiny robots operating inside capillaries. I don't think I need to go over much of the motivation. We've heard about that a bit already in the talks earlier today. But let me just mention a number of issues that come up in how we might get to make these robots and have them useful for us for medicine as opposed to just being conceptual nice ideas. There's questions of how we might fabricate them, how do we control them, how do we power them, identify particular applications for which they will be suitable and able to do things that we're not able at all to do with current medical technologies. I'm focusing today on just the issue of power. And in the context of power, there's really two classes of problems. One, you can think of applications in which the time in which the robot's going to operate is relatively short, and you could put some kind of fuel inside the robot, and that's going to be sufficient for for its task. And the other possibility is for more extended operation, and that's what I'll be focusing on today, in particular looking at chemical fuels that the robots can get from their environment. The particular source of power that I'm going to look at today is oxidizing glucose. This is a particularly appealing method for operation inside the bloodstream because glucose is around and easily available, as well as oxygen. So we're basically going to be talking about having some kind of fuel cells that are similar to what is in some kind of some bacteria that are able to oxidize glucose. And the idea of this study is just to get some kind of quantitative estimates of how much power robots operating in capillaries will have available to them through this method and what sorts of capabilities that amount of power will deliver. So that's going to be the first question. How much power can you expect to have? And of course, the secondary question when you're thinking about medical applications is, would that be safe? Are there some kind of issues that the power generation of the robots would cause for the surrounding tissue or the body? So I'm going to have a look a bit at both of these questions. And the method I'm going to be using is, this is basically a preliminary quantitative engineering design study. And the idea then is to pick a medical application context in a fairly generic one that will likely come up in many different scenarios. If you have other ideas, I'd be more than happy to discuss them and hear about them later. In this particular application, try to identify what are the key constraints on the amount of power available, and then evaluate how much power is available and what might the implications be for the body. So the application I'm going to be looking at basically is robots operating in the bloodstream. So this would be basically for a task where you're having the robot, say, look around for cancer cells or other diagnostic purposes or deliver drugs, and so that they're just patrolling the body for some particular medical either treatment or diagnostics. with the ability for these devices to pass near cells throughout the body. And that can give them a great capability of, say, in particular, say, looking for a small number of cancer cells that might just be starting well before it would be noticed on any kind of much larger scale imaging or diagnosis. I'm going to be focusing, again, just as a specific example of self-assembled groups of these devices on just sitting on a vessel wall, monitoring for interesting chemical signatures or various passing devices, or perhaps it's doing some kind of computation. Now, when we come to glucose and oxygen, the key question is, okay, what's the limiting factor, or the limiting chemical? And if we just look at the chemical reaction for combining glucose and oxygen and the concentrations that are available, we realize basically oxygen is the limiting, the rate limiting chemical. And so that's what I'm going to be focusing on. What is the availability of oxygen? Glucose concentrations typically are much, much higher and will not be the limiting factor. So we realize that most oxygen, of course, is carried in red cells bound to hemoglobin with much higher concentrations than is available in plasma. And so one of the key issues is how does that oxygen come out, and how is that affected by the potential of robots that might be drawing the oxygen and consuming it much more rapidly than the surrounding tissue. So in terms of modeling, we need to look at how does chemical transport get the oxygen from the red cells to the blood, to the plasma, to these devices, and then what is the consequences for power and on the surrounding tissue. There's a number of both modeling challenges as we think of putting together a quantitative model for these devices. And first is complex geometry, the behavior of the cells, and in particular the kinetics of oxygen release from cells. So I'm going to just give you a simplified version of the geometry, just axial symmetric vessels. And this is actually a fairly old model of looking at oxygen transport in microvessels, going back almost 100 years. And so basically you have some tissue surrounding capillaries, and we look then at the behavior within one of these capillaries and the surrounding tissue. And here's basically the idea of having a group of robots that are sitting on the inside wall of a capillary, not big enough to block the vessel, so that the idea is that these are tiny machines that can travel through capillaries. So we're thinking about micron-sized devices, and then they can self-assemble on a capillary wall for some purpose, say, of monitoring or doing some computation. A particular challenge for a model of this behavior is the fact that cells, as they're passing by, are not just static spheres or so. They actually distort in order to go through the capillaries. The cells in their sort of resting configuration are somewhat bigger than the capillaries and distort to go through. And we basically are going to model this following what a number of people have looked at in terms of mechanical studies of how cells go through and distort, to basically see how it is that the cells move by the group of robots that are on the vessel wall. And this is showing you a cross-section. The second issue is to deal with the kinetics of oxygen release from the cells. We might also, in a very simple way, think of red blood cells as like trucks that take oxygen from the lungs to the tissue, but because it's diffusion at the end in the release, the concentration always has to be higher in the cells and the plasma than it is in the tissue. And a consequence of that is that the red blood cells actually take with them a lot of the oxygen they bring in, they can't release because their concentration has to be always higher than it will be in the tissue. So they're not as effective at releasing oxygen as you might think a little truck would be. And this is actually one of the other areas that the respirocytes have an advantage, where they have active pumps and they can put oxygen out and take carbon dioxide in much more effectively than red blood cells, as well as being able to store more of it. So one of the issues is that the robots can have much higher power densities, as we'll see, than is common in tissue. And so they can create much larger gradients in the oxygen concentration than is typical in body tissue. And this raises the question that cells that are carrying a lot of the oxygen, they may pass the robots before they have a chance to release the oxygen. And so kinetics is an important aspect of modeling this behavior. Fortunately, people have looked at this issue, and for the numerical model I'm going to be showing you, we can just go back and make use of some numerical models of how oxygen is released from blood cells as a function of the concentration in the surrounding blood. So the numerical model I'm going to then just be describing takes into account low Reynolds number fluid flow in the small vessels, oxygen transport from the cells, diffusion in the plasma and tissue, and then looks at power generation both in the robots and the surrounding tissue. Now let me then turn to results from this numerical model. And again, the motivation here is to give us an idea of what the kind of capabilities we would expect these machines to have in terms of power, what that enables, and then what might be some of the consequences on the surrounding tissue. I'm going to look at two different scenarios. One you may think of as a fairly low demand scenario when you're just, say, sleeping or resting or sitting here. The other is a high demand scenario when you think of, say, an athlete exercising. Typically, the low demand scenario would be the one that's most relevant in a medical context. You're probably not going to be having high-performing athletes coming in and needing these various medical treatments. But just to get a sense of what the range is, it's good to have both of these scenarios in mind. So first, let's have a look at oxygen transport to these robots. And here again is a cross-section through the tissue and the blood vessel. Here we're looking at a scenario with no robots, just the vessel by itself. And you see the streamlines of the fluid flow, nice and smooth, completely laminar at this tiny scale. And first we'll have a look at the low demand scenario. Again, the case with concentration with no robots. In this case, the red shows the concentration is pretty uniformly high in the blood and the tissue. The tissue is not using very much of the available oxygen. In this case in particular, the blood just has the oxygen. Only small amount of it is actually used by the tissue and just returns to the lungs. We put a group of robots in there, and we see they draw down the concentration quite significantly. And it's particularly the blue goes down to zero. And I want you to notice here is the very high concentration gradients. And this is why kinetics is an important point to keep in this model. Let me show you the similar behavior in a high demand scenario. So this has been very, say, active muscle tissue. This is now without any robots. Again, you see now the tissue is drawing down quite a bit of the oxygen that the blood is delivering. But again, not a lot of it. If you look at the right, there's a lot of oxygen that's just flowing out from this segment of tissue. The tissue is unable to make use of, again, because of diffusion limits. You put the same robots in here, and again, you ask, these robots are just using as much oxygen as diffuses to them and competing with tissue for that. And you see, again, they draw down the oxygen quite a bit. And so we can ask two questions about this. One is how much power the robots get, and two, I'll come back to, is what are the consequences for the surrounding tissue. So first, power for the robots. What we see from this numerical study is that these groups of robots can get about some tens of picowatts. And this is just basically using all the oxygen that diffuses to their surface. And for comparison, the prototypical or nominal typical body cells use from 10 to 1,000 picowatts in their activity. And cells are quite a bit larger than these robots. And just another baseline for comparison of you just sitting here, you're basically using 100 watts is a typical resting power use for a person. So the question is, okay, if we have some tens of picowatts, what could a picowatt be good for one of these robots? And what would these robots be doing? The kinds of things, if they're sitting around, they can be computing some interesting things, measuring some chemical concentrations and so on. A picowatt, even with sort of current laboratory demonstrated nanoscale electronics, so this is not particularly efficient, a picowatt could probably support something like 10 to the 5 logic operations per second. And by today's standards of computation and so on, that's not a lot. But if you compare it to, say, what a nanoparticle or a drug delivery has, which is basically no computation whatsoever, 10 to the 5 operations per second can actually do you some reasonable amount of work on looking for interesting pattern recognition, some trends in concentrations, and so on. This amount of power could also be useful for communication among these robots. And although it's not part of this particular model where they're just sitting on the vessel wall, that kind of a scale of power could also enable these devices to move at about 1 millimeter a second through water or blood plasma by overcoming viscous drag. And that's typical or maybe a little bit faster than the rate that blood will generally flows through capillaries. So that's the results for what's the power from oxygen and glucose available to these robots. Now let me turn to the second question, which is how might this affect the nearby tissue? If you're drawing down too much oxygen, will that mean that the tissue is in big trouble? So some possible questions are you might worry about, well, if the robots are using oxygen, there's less available for the tissue. There could be issues of local heating because of the high power, the high power densities. You might worry about some waste products. That is, if you're consuming oxygen, you're producing more carbon dioxide than normally would be the case. And also the issues of forces on the vessel wall because the robots are sitting there and dealing with fluid drag. I'm just going to look today at the first two of these issues. And so the first one is the robots are competing with the tissue for the same oxygen, and they also, for the section of vessel that they sit on, they're blocking the diffusion of oxygen out of the vessel, and so that could be a concern even if the robots were not using any oxygen at all, if they're just blocking the vessel. So let me go to the most extreme case that I showed you. This was the high demand scenario, and you're having the robots. Again, this is a cross-section through the tissue and the vessel. And let's have a look at the tissue power right next to the vessel and compare it to when the robots are there or not there. And here is a comparison basically both for the low and high demand scenarios. And this compares to what the tissue would produce if oxygen were not limited at all. Sort of basically an infinite availability of oxygen. That's the value of 1 at the top there. And you see that there's a drawdown, especially in the high demand scenario. But if you look at the numbers, actually it's not as dramatic a drawdown in terms of power as it is in terms of oxygen. And this is just because of the way that tissues generate power from oxygen. It's not at all a linear response. Second question is heating. You say, well, gee, these robots have a very high power density compared to cells of several orders of magnitude. Couldn't that cook the surrounding tissue? And so you can use the same model to quantitatively look at what happens with temperature, and indeed the temperature is higher by the robots, but if you actually look at the numbers, it's only a 10 to the minus 4 increase in the temperature. And that's because at these very small sizes, heat is also a diffusive process, diffuses away extremely quickly. And so for hundreds of robots, heating is not likely to be an issue. So let me summarize what I've told you from this model. You can expect tens of picowatts for micron-sized robots operating in capillaries. The oxygen is going to be taken additionally mainly from the passing red cells, relatively small reductions in tissue power, and insignificant local heating. I'd like to wrap up with just some additional biology questions. If any of you have some insights into these, I'd be more than happy to hear your suggestions and comments. There could be some other local effects. What about white blood cells when they go by? There are other functions of the blood than just delivering oxygen, such as immune response and so on. What effect might these robots have on that? And how might the cells on the vessel wall respond to the fact that the robots are sitting there? Are there some longer range effects? So I've talked about lower cell oxygen concentration when the robots take it out. So what happens downstream of where the robots are if the cells don't have as much oxygen? And so for some further information on this model and nanomedicine in general, here are a couple of websites. I particularly recommend the nanomedicine.com that Rob Freitas has put together. Thank you for your attention.
Thank you very much. We've got time now for about, we've got a good 5 minutes for any questions.
Yeah, one. Christian Schaffmeister from Temple University. Glucose is a horribly complicated thing to try and oxidize. It takes many enzymes to do that, and mitochondria and stuff. Have you thought about just if you were breathing hydrogen mixed with oxygen, and what kind of particle pressure of hydrogen you could see in the bloodstream, and then you could just use fuel cell sort of technology to generate power that way?
So I haven't thought about that. It certainly is an interesting suggestion. In fact, is that glucose is around. So there would be a trade-off between how much you want to modify what people are breathing or have available to them versus the complexity of designing what goes on inside these devices. Yeah, thank you for this suggestion.
Blumberg from Philadelphia. We've several speakers have talked about other constituents of the blood that would be encountered by these nano robots. What about things like viruses, for example, or or parasites, malaria parasites? And now, mind you, I think this is a concern that's some years in the future. But has there been any modeling or consideration of those? These would be common in areas where in viruses, bloodborne viruses are common, or where malaria or filaria, for example, which have pretty good size objects in the blood.
So that's an excellent question. There's been no modeling work at all on that. Even in the simpler case of what I mentioned in terms of just what about white blood cells passing by, there hasn't been any modeling on that with respect to these robots. But yeah, certainly many things to look at.
Oh, thank you. There was so much information there, and I think I blinked. But was this modeling based on complete oxidation of the glucose to carbon dioxide in water, or on a fraction of the energy that could be obtained, say, from a single enzymatic reaction in glucose oxidation?
So in this case, this model was based on the complete oxidation, but then accounting for a factor of a fairly low efficiency on how those how much of that power would actually be captured by the devices. So when I talked about tens of picowatts available, and then say, well, what could the robot get from just 1 picowatt? There I was then thinking that there's lots of efficiency issues, and you might not be able to actually harness all the power that's available there. So that in one sense, it's looking at what is the potential, and then cutting it by a factor, say, of 10 to say what you might actually have available.
Thanks.
Yeah.
Great. Thank you very much,
Thank you.
Dr. Hogg. Well done. Very well done. Good show for Institute for Molecular Manufacturing.